The morning of June 4th, 1942, 15,000 feet above the Pacific Ocean, northwest of Midway Atoll, Lieutenant Commander Wade McCluskey squinted through the greenhouse canopy of his Douglas SBD Dauntless, searching an empty ocean that should have been full of Japanese carriers. His fuel gauge was dropping toward the point of no return. Behind him, 31 other Dauntlesses from the USS Enterprise followed in formation, their Wright Cyclone engines churning through precious gasoline with every passing minute. McCluskey had launched 2 hours earlier, with what intelligence promised would be perfect coordinates to intercept Admiral Nagumo's carrier strike force. But the ocean below revealed nothing except endless blue swells reflecting morning sunlight. No carriers, no destroyers, no wake trails. The Japanese fleet had vanished. Every pilot in his formation understood the mathematics of their situation with brutal clarity. They had perhaps 20 minutes of fuel, remaining before the decision became irrevocable. Turn back now toward Enterprise and they might make it home. Continue searching and they would all end up swimming. Then McCluskey spotted something that changed everything. A single destroyer, far below, cutting a white wake as it raced northwest at flank speed. The Japanese destroyer Arashi, though McCluskey didn't know its name, was hurrying to rejoin the main fleet after depth charging the American submarine Nautilus. McCluskey made the decision that Admiral Nimitz would later call one of the most important of the entire battle. He turned northwest and followed the destroyer's wake. 10 minutes later, at approximately 1000 hours, McCluskey's radioman called out the sighting every American pilot in the Pacific had been hunting for 9 months. 4 Japanese aircraft carriers steaming in formation, their flight decks crowded with aircraft being rearmed and refueled. The carriers Akagi, Kaga, Soryu, and Hiryu. The same 4 carriers that had devastated Pearl Harbor on December 7, 1941, the most powerful naval strike force ever assembled, and they were completely vulnerable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What happened in the next 6 minutes would validate a radical bombing technique that Japanese naval commanders had dismissed as tactically impossible. The Americans were about to demonstrate that an aircraft could attack from altitudes so extreme that defending gunners could barely track them, diving at angles so steep that fighters couldn't intercept, and still deliver bombs with devastating accuracy. The SBD Dauntless, nicknamed slow but deadly by its pilots, was about to prove that precision mattered more than speed, that geometry could defeat firepower, and that the most feared fleet in the Pacific could be destroyed by an aircraft the Japanese had considered obsolete. The journey to this moment of impossible violence had required American engineers to solve a problem that had plagued dive bombers since their inception. How do you drop straight down from 3 miles up without either ripping your aircraft apart or missing your target completely? In 1935, when the Northrop Corporation began designing what would become the Dauntless, dive bombing was still a relatively new tactical concept. The idea seemed simple enough on paper. A bomber approaching from high altitude could theoretically achieve much greater accuracy by diving directly at the target rather than attempting to hit it from level flight. But the practical execution created seemingly insurmountable problems. An aircraft diving from 15,000 feet would accelerate rapidly under gravity. Without some method of controlling speed, the dive bomber would quickly exceed its structural limits. Wings would tear off, control surfaces would flutter and fail. The aircraft would simply disintegrate in mid-air from aerodynamic forces. If a pilot tried to slow the dive by pulling back on the stick, the increased angle of attack would generate enormous G-forces that could either crush the pilot into unconsciousness or break the airframe. The alternative was pulling out at a much higher altitude to avoid excessive speed and G-loading. But pulling out higher meant releasing bombs from greater distance, which destroyed the accuracy advantage that made dive bombing worthwhile in the first place. The German Luftwaffe had attacked this problem with the Junkers Ju-87 Stuka, which used fixed dive brakes that deployed automatically. The Stuka could dive steeply and even recover automatically if the pilot blacked out under G-forces, but the Stuka was desperately slow, vulnerable to modern fighters, and lacked the range for Pacific operations. Ed Heinemann and his design team at Douglas Aircraft approached the problem from first principles. They needed an aircraft that could dive at 70 to 80 degrees from vertical, nearly straight down, while maintaining a constant speed of approximately 240 knots. That constant speed was absolutely critical. Too fast and the pull-out would kill the pilot or break the aircraft. Too slow and the bomber would become an easy target for anti-aircraft fire and intercepting fighters. The solution they developed was ingenious and would prove decisive at Midway. Perforated split dive brakes. The dive brakes were built directly into the trailing edge of each wing. When deployed, they split apart like opening Venetian blinds. The upper surface hinged upward. The lower surface hinged downward. But unlike solid air brakes, these flaps were perforated with thousands of precisely calculated holes, each 3 inches in diameter. The perforations solved multiple problems simultaneously. They created enormous aerodynamic drag, slowing the aircraft like a parachute. But the holes allowed controlled airflow through the brakes, preventing the turbulent buffeting that solid flaps would generate. The perforations stabilized the aircraft, making it rock-steady even in a near-vertical dive. The hydraulic system that deployed these brakes was robust and reliable, tested through thousands of practice dives. When a Dauntless pilot pushed the dive brake lever forward, hydraulic pressure forced the split flaps open against the airstream. The effect was immediate and dramatic. An aircraft that might accelerate to over 400 knots in an uncontrolled dive would hold steady at 240 knots, with brakes deployed. The pilot could point the nose almost straight down, and the Dauntless would descend in a controlled, stable dive that felt more like riding an elevator than hurling toward the earth. This stability transformed bombing accuracy. In a stable 70-degree dive with constant airspeed, a pilot could keep his bombsight crosshairs precisely on target throughout the entire descent. The bombsight was a simple telescopic device, magnifying 3 times, mounted directly over the instrument panel where the pilot could see it clearly. The bombardier's job in larger aircraft was handled by the pilot himself in the Dauntless. The technique required training and nerve, but the physics were predictable. At 70 degrees, the aircraft covered vertical distance quickly while moving relatively slowly across the ground. This gave the pilot more time to correct his aim, more time to compensate for target movement, more time to ensure perfect alignment before bomb release. The Dauntless was built to withstand the stresses of this violent maneuver. The airframe was stressed to handle up to 9 Gs during the pullout from a steep dive. The wing structure used a compact, rigid design without folding mechanisms. This made deck handling more difficult on crowded carrier decks, but it created a wing that was extraordinarily strong and resistant to combat damage. The Wright R-18 2060 Cyclone radial engine produced 1,200 horsepower, enough to pull the aircraft out of even the steepest dives while carrying a 1,000-pound bomb under the fuselage. The engine was reliable, maintainable under difficult field conditions, and capable of sustained operation even after battle damage. Armament was practical rather than overwhelming. 2 50-caliber Browning machine guns mounted in the engine cowling provided forward firepower for strafing or engaging enemy fighters. The rear seat gunner operated twin 30-caliber Browning machine guns on a flexible mount, providing defensive fire against pursuing fighters. Japanese Zero pilots learned quickly to respect that rear gunner. As long as those guns were firing, approaching Zeros tended to break off their attacks before reaching killing range. Once the gunner was hit and those guns fell silent, the Dauntless became far more vulnerable. The bomb load was simple but devastating. A single 1,000-pound bomb mounted under the fuselage on a displacement gear that swung the bomb outward and downward when released, ensuring it cleared the propeller arc during a steep dive. 2 smaller bombs, typically 250 pounds each, could be mounted under the wings for secondary targets. That 1,000-pound bomb was the weapon that would sink carriers at Midway. The Mark 13 general-purpose bomb, filled with Torpex explosive, could penetrate a carrier's wooden flight deck, detonate inside the hangar deck among fully fueled and armed aircraft, and create a catastrophic internal explosion that no damage control team could contain. By the spring of 1942, American pilots had refined their dive bombing technique into a precise, repeatable procedure that exploited every advantage the Dauntless could provide. The attack profile they developed at Midway would become doctrine for the rest of the war. Pilots approached targets at altitudes between 14,000 and 20,000 feet, high enough to be difficult for anti-aircraft gunners to track accurately, high enough that defending fighters needed several minutes to climb to intercept altitude. The formation would fly in stacked echelons, each section slightly below and offset from the section ahead, ensuring every pilot had a clear view of the target without risking collision during the dive. As the target approached, pilots would increase engine RPM to full power and select a low blower on the supercharger. They didn't need high-altitude power for the pullout, which would occur close to sea level. When the target began to disappear under the nose of the aircraft, the pilot pushed the stick forward firmly. The Dauntless nosed over into the dive. The pilot felt himself rising slightly out of his seat as negative G-forces took effect. Loose objects in the cockpit began to float. Then came the critical moment. The pilot deployed the dive. Brakes. The perforated split flaps opened with hydraulic smoothness. The aircraft immediately stabilized at its terminal velocity of approximately 240 knots. The dive angle was typically 70 degrees, almost but not quite vertical. At this angle, the aircraft descended at over 3,000 feet per minute, while moving relatively slowly horizontally. The view through the bomb sight was extraordinary and terrifying. The target grew larger with every second. The pilot could see individual aircraft on the carrier deck, individual crewmen running across the flight deck, individual anti-aircraft gun positions tracking upward trying to find the diving bomber. The key was holding the dive until the last possible moment. Releasing too early sacrificed accuracy. Releasing too late meant insufficient altitude to pull out safely. The standard release altitude was between 1,500 and 2,000 feet above the target. At 240 knots, that gave the pilot approximately 3 to 4 seconds from release to impact, enough time to initiate pullout, but not enough time for the target to maneuver significantly. At release altitude, the pilot hit the bomb release button. The displacement gear swung the 1,000-pound bomb outward and downward, clear of the propeller. Simultaneously, the pilot retracted the dive brakes and hauled back hard on the stick. The Dauntless entered its pullout, the moment of maximum stress on the airframe and pilot both. G-forces built rapidly. 3 Gs, 4 Gs, sometimes 5 Gs in an aggressive pullout. The pilot's vision began to narrow as blood drained from his brain. Grey tunnel vision crept in from the edges. But the Dauntless was built for this. The airframe held. The wings stayed attached, and the bomb continued downward toward its target at terminal velocity while the aircraft curved away in its pull-out arc. From release to impact, those 3 to 4 seconds felt eternal. The pilot couldn't watch the bomb strike. He was fighting G-forces, fighting to maintain consciousness, fighting to keep the aircraft under control as it transitioned from dive to level flight at high speed just above the waves. The rear gunner, if he had the presence of mind and wasn't fighting off pursuing Zeros, might glimpse the bomb's impact. A flash, an explosion, smoke and flame erupting from the target. But confirmation would come later, from reconnaissance photographs or from other pilots who'd completed their dives and could see the damage. This was the technique that Wade McCluskey's dive bomber squadrons brought to bear against the Japanese carriers on the morning of June 4, 1942. The Japanese defenders were expecting torpedo attacks from low altitude, which their Zeros excelled at intercepting. They were expecting horizontal bombing from high altitude, which was easy to evade through ship maneuvering. They were not expecting, and their defensive doctrine had not prepared them for, near-vertical dive bombing attacks from 15,000 feet delivered by aircraft that could hold rock-steady aim throughout a 70-degree dive. The Japanese carriers had launched their own strike against Midway Atoll at dawn. That strike had inflicted damage but failed to completely suppress the airfield. Now, as those strike aircraft returned to the carriers, the Japanese faced a critical decision. Should they rearm their aircraft for a second strike against Midway, or should they rearm for an anti-ship strike against American carriers that scout planes had just reported? Admiral Nagumo had ordered his strike aircraft rearmed with anti-ship weapons, torpedoes, and armor-piercing bombs. Then he'd reversed the order as the Midway strike force ran low on fuel and needed to land immediately. The flight decks and hangar decks of all four carriers were cluttered with aircraft being refueled, with bombs and torpedoes stacked on deck carts, with fuel hoses snaking across the wooden decks. It was the most dangerous possible configuration, and it was exactly at this moment that the American dive bombers appeared overhead. McCluskey's Enterprise squadrons, 32 Dauntlesses from Bombing 6 and Scouting 6, arrived almost simultaneously with 17 Dauntlesses from Yorktown's Bombing 3. The timing was pure coincidence, the result of navigation choices made independently by squadron commanders searching for the same target. But the effect was overwhelming concentration of force that Japanese Combat Air Patrol Zeros couldn't possibly stop. McCluskey assigned targets with hand signals visible to following pilots. He would take his squadrons against Kaga and Akagi, the two nearest carriers. Yorktown's squadron under Lieutenant Commander Maxwell Leslie would attack Soryu. The Dauntlesses pushed over into their dives at 22 minutes past 10 in the morning. The Japanese gunners saw them coming, tiny specks against the bright sky that suddenly grew larger, as they pitched into near-vertical dives. Anti-aircraft fire began immediately, black puffs of exploding shells filling the sky. But 70-degree dive angles created an almost impossible gunnery problem. The aircraft were descending so steeply that gun crews had to elevate their weapons to extreme angles, making tracking and leading almost impossible. A barrage fired at a predicted intercept point might work against aircraft in shallow glides, but Dauntlesses in steep dives transited through any given altitude in just seconds, too fast for barrage fire to be effective. The few Zeros that tried to intercept the diving bombers discovered another problem. At 70-degree dive angles and high closing speeds, the geometry of pursuit attacks became nearly impossible. A Zero pilot trying to match the dive angle found his aircraft accelerating uncontrollably without dive brakes. If he tried to attack from the side, the closing speed was so high he had perhaps 1 second of firing. Opportunity before overshooting. Lieutenant Richard Best led Bombing 6's first section of 3 aircraft against Akagi, Admiral Nagumo's flagship. Best held his dive until 1,800 feet, closer than doctrine recommended but necessary for absolute certainty. His 1,000-pound bomb struck Akagi's flight deck just aft of the midship elevator. The bomb penetrated the wooden deck and detonated inside the hangar, among fueled and armed aircraft. The explosion touched off a cascade of secondary detonations that tore through the hangar deck. Fires erupted immediately, fed by avgas from ruptured fuel lines and burning aircraft. Damage control teams rushed toward the flames, but the fires were already beyond control. A second bomb from Best's section struck Akagi's portside near the aft elevator. More explosions, more fires. Within minutes, Akagi was burning from amidships to stern. Simultaneously, other sections from Enterprise attacked Kaga. Multiple bombs struck the carrier in rapid succession. One bomb hit near the forward elevator, penetrating the hangar deck. Another struck the flight deck amidships. A third hit near the island superstructure. Each bomb detonated among the cluttered aircraft, the stacked ordnance, the fuel hoses. Kaga erupted in a series of massive explosions that sent aircraft parts and debris flying hundreds of feet into the air. The flight deck buckled and warped from internal explosions. Fires spread through the hangar deck, reaching the aviation fuel storage tanks. Explosions continued every few minutes as more ordnance cooked off in the heat. Within 5 minutes of the first bomb hit, Kaga was a burning wreck, dead in the water, with fires raging out of control throughout her length. 3 miles away, Yorktown's squadron attacked Soryu. 17 Dauntlesses dove on the carrier from 15,000 feet. At least 3 bombs struck the carrier's flight deck and penetrated to the hangar. Soryu's fate was identical to her sister's. Internal explosions among armed aircraft, cascading fires, secondary detonations. The wooden flight deck caught fire and began burning. Damage control was impossible. The fires fed themselves on aviation fuel and ordnance. Soryu was doomed minutes after the first bomb struck. 3 carriers fatally wounded in approximately 5 minutes. The most decisive 5 minutes of naval warfare in the Pacific. The Dauntless dive bombers had achieved what months of American torpedo attacks, submarine attacks, and high-altitude bombing had failed to accomplish. They had destroyed the core of Japan's carrier striking power in a single coordinated attack. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But understanding why this attack succeeded requires understanding what made it different from every previous American attack. The key was altitude and angle. American torpedo bombers attacking at sea level could be intercepted by Zero fighters with devastating effectiveness. The Battle of Midway demonstrated this brutally. 3 American torpedo squadrons, flying TBD Devastators, attacked the Japanese carriers between 9:30 and 1000 hours that morning, just minutes before the dive bombers arrived. Of 41 Devastators launched, only 6 survived to return to their carriers. None scored any torpedo hits. The Zeros massacred them. Flying low and slow, the Devastators were perfect targets. Zero pilots could dive on them from above with enormous speed advantage. The torpedo planes couldn't maneuver aggressively while maintaining their attack run, and without dive breaks, the Zeros could easily match the Devastators' speed and position for sustained gunfire. High-altitude level bombing also proved almost completely ineffective. Army Air Force B-17 flying fortresses from Midway Atoll attacked the Japanese carriers from 20,000 feet that same morning. They dropped hundreds of bombs. Not a single one hit a maneuvering carrier. The carriers could see the bombs falling from such altitude and had plenty of time to change course and speed, evading every bomb. But dive bombing from 15,000 feet at 70-degree angles created conditions the Japanese couldn't counter. The dive bombers appeared suddenly overhead, too high for effective Zero interception in the critical first moments. Once committed to their dives, they descended so quickly that Zeros couldn't position for sustained attacks. The steep dive angles made anti-aircraft tracking almost impossible, and most critically, the bombs took only 3 to 4 seconds to fall after release, giving carriers almost no time to maneuver away from the impact point. The Japanese had not prepared for this attack profile because their own naval aviation doctrine emphasized torpedo attacks and horizontal bombing. Japanese dive bombers existed, the Aichi D-3 Val, but Japanese doctrine used them primarily for short-range attacks with shallow dive angles. The concept of 70-degree hell diving from extreme altitude was not part of Japanese tactical thinking. Their carriers' anti-aircraft defenses were designed to engage torpedo planes at sea level and fighters at medium altitude. They had inadequate weapons positioned for high-angle fire against steep dive-bombing attacks. The surprise was complete and total. The 3 burning carriers, Akagi, Kaga, and Soryu, represented Japan's most experienced carrier aviation force. These were the carriers that had struck Pearl Harbor. These were the carriers that had dominated the Pacific for 6 months. And now they were burning wrecks, their flight decks impassable, their hangars filled with fires that couldn't be contained, their crews abandoning ship or fighting hopeless battles against flames. The 4th carrier, Hiryu, had been separated from the main formation and escaped the initial attack. But her survival would be measured in hours, not days. American reconnaissance planes would find her. More Dauntless dive bombers would attack from 15,000 feet at 70-degree angles, and Hiryu would join her sisters at the bottom of the Pacific. The weapon that accomplished this devastating transformation wasn't superior speed. The Dauntless was genuinely slow compared to most combat aircraft, with a maximum speed of just 255 miles per hour. It wasn't superior firepower. Two 50 caliber guns and two 30 caliber guns were adequate, but not overwhelming. It wasn't advanced technology. The basic Dauntless design dated to 1935 and used conventional materials and manufacturing throughout. The decisive advantages were precision and technique, those perforated dive brakes that allowed rock-steady 70-degree dives. That 1,000-pound bomb mounted on a displacement gear that ensured clean separation. That telescopic bomb sight that let pilots aim throughout the entire dive. And, most important, the tactical doctrine that emphasized attacking from extreme altitude at angles no defending force was prepared to counter. The results at Midway validated everything American naval aviation had learned about dive bombing through years of peacetime practice and months of desperate combat experience. But the story of how the Dauntless reached this level of effectiveness reveals a harder truth about innovation in warfare. The Japanese had seen dive bombing before Midway. They'd experienced it, they'd analyzed it, and they'd made a calculated decision that it didn't represent a primary threat requiring defensive countermeasures. Japanese carrier designers had prioritized speed and offensive capability over defensive armor. The flight decks were constructed of wood planking over steel frames, light enough to maintain high ship speeds but vulnerable to bomb penetration. Hangar decks were open spaces designed for rapid aircraft handling with minimal internal compartmentalization that might slow the spread of fires. Japanese carriers could launch and recover aircraft faster than American carriers. They could turn faster, maneuver more aggressively, and maintain higher sustained speeds. These were deliberate design choices, optimizing for offensive operations. The Japanese naval philosophy through 1942 emphasized that the best defense was overwhelming offense. Carriers should strike first, strike hard, and destroy enemy carriers before they could launch their own attacks. In the battles of the Coral Sea and the Indian Ocean, this philosophy had worked exactly as designed. Japanese carriers had repeatedly struck first and devastated opposing forces. But at Midway, American dive bombers achieved something that Japanese planning had considered nearly impossible. They reached attack positions above the Japanese fleet without being detected early enough for an effective response. The Japanese Combat Air Patrol consisted of approximately 36 Zero fighters orbiting at various altitudes around the carrier formation. These fighters had been fully occupied intercepting American torpedo bombers attacking at wave-top height between 9:30 and 1000 hours. When McCluskey's dive bombers appeared at 15,000 feet just minutes later, most of the Zeros were at low altitude, low on ammunition, and many were landing to refuel and rearm. The few Zeros at high altitude simply didn't have enough time or numbers to intercept over 30 American dive bombers pushing into their attack dives simultaneously. Japanese radar technology in 1942 was primitive compared to American and British systems. Japanese carriers had basic air search radars, but the systems provided limited altitude information and poor resolution. Radar operators might detect a formation of aircraft approaching, but determining exact altitude, speed, and attack profile was difficult or impossible. Visual lookouts remained the primary detection method. By the time lookouts spotted the dive bombers overhead and sounded the alarm, the attack was already developing. Admiral Nagumo himself was on Akagi's bridge when the dive bombers attacked. Multiple accounts from surviving officers describe the scene, lookouts suddenly shouting and pointing upward, officers raising binoculars toward the sky, the terrible realization that American aircraft were already in their dives. Nagumo issued orders to increase speed and turn hard to port, attempting to maneuver all four carriers away from the falling bombs. But at 70-degree dive angles, with release altitudes below 2,000 feet, the bombs were falling for only seconds after release. There simply wasn't enough time for a 30,000-ton carrier to accelerate or turn fast enough to evade. The first bomb struck Akagi at approximately 10:22 in the morning. Nagumo was thrown to the deck by the explosion. Smoke immediately began, pouring up through the flight deck from the hangar below. More explosions followed as secondary detonations rippled through the ship. Within minutes, Fires were beyond the capacity of damage control teams to contain. The admiral's staff evacuated him to a destroyer. Akagi would burn for hours before being scuttled by Japanese destroyers firing torpedoes to ensure she sank. Kaga absorbed 4 bomb hits in the first minute of the attack. One bomb struck directly on the forward elevator, jamming it in the raised position and creating a chimney that fed oxygen to fires below. Another bomb detonated on the flight deck near the island superstructure, killing most of the senior officers stationed there instantly. The carrier's captain, Jisaku Okada, was mortally wounded. Fires spread so quickly that many crew members trapped below decks never reached escape routes. Kaga would eventually suffer a massive internal explosion that broke her back. She sank at approximately 7:25 that evening, taking over 800 crewmen with her. Soryu took 3 direct bomb hits within 2 minutes. The first bomb penetrated near the forward elevator and detonated among aircraft being refueled on the hangar deck. The explosion touched off aviation fuel that had been carelessly spilled during the rushed rearming operations. Burning fuel spread across the hangar deck, igniting more aircraft. The second bomb struck amidships, penetrating to the hangar and adding more explosive force to the growing conflagration. The third bomb hit near the island, destroying communications equipment and killing senior officers. Soryu's captain, Ryusaku Yanagimoto, chose to go down with his ship. He was last seen standing on the bridge as the carrier settled into the water at approximately 7:13 that evening. The tactical achievement at Midway went beyond simply sinking carriers. The dive bomber attack demonstrated that a numerically inferior force, using superior tactics and technique, could overcome a stronger enemy. The American carriers at Midway had launched fewer total aircraft than the Japanese. American fighters, the F-4F Wildcat, were demonstrably inferior to the Zero in most performance metrics. American torpedo bombers were obsolete and suffered catastrophic losses, but the dive bombers, using the specific capabilities built into the Dauntless design, achieved results that balanced the entire battle. Japanese naval commanders studying the battle results reached several conclusions that would influence their defensive doctrine for the remainder of the war. First, carriers needed better anti-aircraft defenses specifically optimized for high-angle fire against steep dive bombing attacks. Second, combat air patrols needed better coordination and altitude discipline to maintain fighters at high altitude, even while responding to low-altitude threats. Third, carrier damage control procedures needed complete revision to handle the catastrophic internal fires that resulted from bomb hits on crowded hangar decks. But these lessons came too late to change the strategic situation. Japan had lost 4 of its 6 fleet carriers in a single day. The remaining carriers, Shokaku and Zuikaku, were not enough to maintain offensive operations across the vast Pacific theater. American industrial production was already accelerating, with new Essex-class fleet carriers under construction. The balance of power had shifted irreversibly at Midway, and the SBD Dauntless dive bomber had delivered the decisive blows. The pilots who flew those missions understood what they'd accomplished, but many didn't live to see the war's end. Of the 32 Dauntlesses from Enterprise that attacked at Midway, 4 were shot down during the battle. Several more pilots were killed in subsequent battles. Wade McCluskey survived the war but was badly wounded during a later action when his Dauntless was hit by anti-aircraft fire. He spent months recovering from burns and wounds before returning to limited duty. Richard Best, who led the attack on Akagi, was diagnosed with tuberculosis shortly after Midway, after accidentally inhaling caustic soda fumes from his defective oxygen system during the mission. He never flew combat again. The Dauntless itself continued serving throughout the Pacific War. It participated in every major carrier battle through 1944. At the Battle of the Philippine Sea in June 1944, nicknamed the Great Marianas Turkey Shoot, Dauntlesses helped destroy 3 Japanese carriers and multiple supporting vessels. By late 1944, the Dauntless was being replaced by the larger, faster Curtiss SB-2C Helldiver, but many pilots preferred the older Dauntless, which they considered more reliable and easier to fly. The Helldiver was faster and carried a heavier bomb load, but it was also more difficult to maintain and more demanding to operate from carrier decks. Total production of the SBD Dauntless reached 5,936 aircraft by the time manufacturing ended in July 1944. Douglas built 4,024 aircraft at its El Segundo, California plant. Douglas built another 900 in Tulsa, Oklahoma. The Navy ordered another 1,112 units, but cancelled the order as the Helldiver replacement accelerated. The final production variant, the SBD-6, incorporated numerous minor improvements learned from combat experience. A more powerful engine producing 1,350 horsepower, additional armor protection for the pilot and gunner, improved fuel capacity for extended range, better radio equipment for coordination. But the fundamental design remained essentially unchanged from 1941 through 1944. The perforated dive brakes, the displacement bomb rack, the rugged airframe. These core features that enabled 70-degree dive bombing from extreme altitude remained constant because they worked. Engineers occasionally proposed improvements, but combat pilots consistently reported that the basic Dauntless did exactly what they needed. Don't fix what isn't broken. The statistical record of Dauntless achievements speaks to its effectiveness. Dauntless squadrons sank or heavily damaged 6 Japanese carriers during the war: Akagi, Kaga, Soryu, and Hiryu at Midway, Shoho at the Battle of the Coral Sea, Hio at the Battle of the Philippine Sea. These 6 carriers represented the core of Japan's naval aviation striking power. Additional Dauntless attacks damaged Shokaku at Coral Sea and badly damaged Zuikaku at multiple battles, keeping both carriers out of action for months at critical moments. Beyond carriers, Dauntlesses sank numerous cruisers, destroyers, submarines, and transports. They destroyed shore installations, attacked ground forces, and provided close air support for amphibious landings. One analysis calculated that Dauntless dive bombers accounted for more Japanese shipping tonnage destroyed than any other Allied aircraft type in the Pacific theater. The total exceeded 1 million tons of warships and merchant vessels sunk or damaged. The effectiveness came from that fundamental capability, the ability to dive nearly vertically from 15,000 feet while maintaining rock-steady aim and deliver a 1,000-pound bomb with accuracy measured in feet rather than yards. Japanese ships could maneuver away from torpedo tracks they could see approaching. They could evade bombs dropped from 20,000 feet that took 20 or 30 seconds to fall. But they couldn't evade a bomb released at 1,800 feet that struck 3 seconds later. The perforated dive brakes that made this precision possible represented one of those elegant engineering solutions that seems obvious in retrospect, but required genuine insight to develop originally. Ed Heinemann's design team at Douglas had tested dozens of fine configurations before arriving at the perforated split-flap design. Solid flaps created too much turbulence and made the aircraft difficult to control. Single-surface flaps generated asymmetric forces. Various perforation patterns created different drag and stability characteristics. The final design, with 3-inch diameter holes in a specific pattern and spacing, emerged from methodical testing in wind tunnels and flight trials. That testing process took years of peacetime development work. The XBT-2 prototype first flew in April 1938. The production SBD-1 entered squadron service in June 1940. Pearl Harbor occurred 18 months later. Those 18 months of squadron training, of pilots learning the dive bombing technique, of maintenance crews learning the systems, proved essential. When war came, the Dauntless and its pilots were ready. The Japanese had comparable aircraft in technical terms. The Aichi D-3A Val dive bomber entered service in 1940 and participated in the Pearl Harbor attack. The Val had retractable landing gear for reduced drag. It had a more powerful engine than early Dauntless models. But Japanese dive bombing doctrine emphasized shallow dive angles, typically 45 to 50 degrees rather than the 70-degree dives American pilots routinely flew. This doctrinal difference reflected different naval philosophies. Japanese doctrine emphasized speed of attack and rapid egress. American doctrine emphasized accuracy and accepted the time required for steep diving approaches. At 45-degree dive angles, the VAL remained relatively fast and maneuverable. Pilots could begin their pullout at higher altitude with lower G-forces. The attack took less time from pushover to bomb release, but accuracy suffered compared to steep diving attacks. At 70-degree angles, American pilots could keep their bomb sights centered on target throughout the dive. At 45 degrees, the target moved across the bomb site more quickly, requiring more pilot skill to maintain accurate aim. The difference showed in combat results. American dive bombers consistently achieved higher hit percentages than their Japanese counterparts in similar attack conditions. The psychological impact of 70-degree diving attacks affected both attackers and defenders. Pilots diving almost straight down experienced extreme sensory overload. The target rushed up at terrifying speed. The altimeter unwound rapidly. The wind noise increased to a scream. Peripheral vision blurred. Some pilots described a sensation of time distortion, where the dive seemed to last forever and also be over in an instant. Pulling out of the dive created different sensations. As G-forces built during the pullout, blood drained from the brain toward the lower body. Vision narrowed into a grey tunnel. Some pilots experienced complete greyout or brief blackout if they pulled too aggressively. The aircraft groaned and creaked as structural members took maximum loading. Occasionally, rivets would pop loose from the stress, leaving small holes in the aluminum skin. For Japanese sailors on the receiving end, the experience was equally terrifying. The dive bombers appeared suddenly overhead as small dots against the sky. Within seconds, they grew into identifiable aircraft shapes, wings vertical, noses pointed directly downward. The sound of engines was initially faint, then grew to a howling scream as the aircraft accelerated downward. Anti-aircraft guns would track upward, firing desperately, creating black puffs of exploding shells. But the bombers kept coming, seemingly unstoppable, until they released their bombs and pulled away in violent turns. The bombs themselves made a distinctive whistling sound as they fell. Japanese sailors learned to recognize that sound and knew they had perhaps 2 seconds between hearing the whistle and the explosion. 2 seconds to throw themselves flat, to grab something solid, to pray. Then the impact, the blast wave, the shower of debris and shrapnel. Multiple survivors' accounts describe the psychological terror of being dive-bombed, the feeling of helplessness watching the aircraft dive directly at your position, the certainty that the bomb was aimed at you specifically, the inability to do anything but wait for impact or miracle. Some men froze. Others panicked and ran, even though running was useless against a bomb that might strike anywhere across the ship. The steady veterans stayed at their positions, continued working, and accepted their fate with stoic discipline. But everyone was afraid. That fear was completely rational. A 1,000-pound bomb exploding anywhere near you would kill you instantly or leave you horribly wounded. The material effect of that 1,000-pound bomb went beyond the immediate explosion. When a bomb penetrated a carrier flight deck and detonated on the hangar deck, the blast wave propagated through the enclosed space with devastating effect. Aircraft parked on the hangar deck absorbed some of the blast energy, but they also became secondary projectiles. Wings and fuselages were torn apart and hurled across the hangar, destroying other aircraft and killing crew members. Fuel tanks ruptured, spreading aviation gasoline that ignited instantly from hot metal fragments. Ammunition began cooking off, adding explosions to the fire. Bombs and torpedoes stacked on handling carts were particularly dangerous. If the heat reached them, they could detonate in sympathetic detonation, adding enormous explosive force to the existing fires. Japanese carriers at Midway experienced this exact cascade of destruction. The initial bomb hits weren't immediately fatal to the ships themselves. The hulls remained intact. The engines continued operating. but the internal fires on the hangar decks quickly became uncontrollable. Damage control teams tried desperately to fight the flames, but aviation fuel fires burn at extremely high temperatures and spread rapidly. Water applied to gasoline fires can actually spread the flames as the floating fuel disperses across the water surface. Foam suppression systems existed, but carrier hangar decks in 1942 typically had inadequate foam capacity for major fires. The fires burned until they consumed all available fuel, which meant they burned through entire aircraft inventories plus stored fuel reserves. As fires raged unchecked, they heated the steel structure of the ship. Eventually, steel beams and deck plates heated to temperatures where they lost structural strength. Decks sagged and collapsed, bulkheads buckled. The ship's structural integrity progressively failed. This was the ultimate fate of all 4 Japanese carriers at Midway. They didn't sink quickly from the initial bomb damage. They burned for hours, growing progressively weaker until their structures failed and they settled into the ocean. Akagi burned for over 12 hours before being scuttled. Kaga burned for 9 hours. Soryu burned for 7 hours. Hiryu, attacked later in the afternoon by another wave of Dauntless dive bombers from Enterprise, burned through the night and sank early the next morning. The human cost was staggering. Kaga lost over 800 crew members. Kagi lost approximately 260. Soryu lost approximately 720. Kairyu lost over 400. Thousands more were wounded, many with horrific burn injuries that 1942 medical care couldn't adequately treat. Many wounded men died days or weeks later from infections or burn complications. The psychological trauma affected survivors for the rest of their lives. Men who'd thought themselves invincible aboard the finest carriers in the world had watched those carriers burn and sink beneath them. American losses were also severe, though less than Japanese casualties. The torpedo squadrons had been nearly annihilated. Torpedo Squadron 8 from Hornet lost all 15 aircraft and 29 of 30 crew members. Only Ensign George Gay survived, floating in the ocean for 30 hours before rescue. The dive bomber squadrons lost fewer aircraft but still suffered significant casualties. Anti-aircraft fire downed several Dauntlesses during their attacks. Zero fighters shot down several more during the egress. Some damaged aircraft ditched in the ocean when they ran out of fuel trying to return to their carriers. Total American aircraft losses at Midway exceeded 150 planes. Over 300 aviators were killed or captured, but the strategic exchange was overwhelmingly favorable for the Americans. The loss of 4 carriers and their experienced air groups crippled Japanese offensive capability. The United States could replace lost aircraft and train new pilots through industrial and training capacity that Japan couldn't match. By late 1942, new American carriers were entering service, while Japanese carriers remained in short supply. The initiative in the Pacific shifted permanently at Midway, and the SBD Dauntless had delivered the decisive blow. The innovation that made this possible wasn't a single brilliant invention. It was a system of complementary technologies and techniques that worked together: perforated dive brakes for speed control, displacement bomb gear for clean separation, rugged airframe stressed for high G pullouts, reliable engine with adequate power, simple but effective bomb sight, systematic training for pilots in the specific technique of 70-degree diving attacks, tactical doctrine emphasizing attacks from extreme altitude to minimize interceptor effectiveness. Each element was necessary. Remove any single element, and the system failed or operated at much reduced effectiveness. This integrated approach to weapon system development would characterize American military innovation throughout World War II. The B-29 bomber combined pressurized crew compartments, remote-controlled gun turrets, high-altitude performance, and heavy bomb load into a weapon system that could strike Japan from extreme range. The proximity fuse combined miniaturized radar, reliable electronics, and production engineering into an artillery shell that revolutionized anti-aircraft effectiveness. The Jeep combined simplicity, durability, and mass production into a vehicle that mechanized American logistics. In each case, the achievement came from systematic integration of multiple technologies rather than single breakthrough innovations. The Dauntless represented this approach applied to carrier aviation. It wasn't the fastest dive bomber, it wasn't the most heavily armed, it wasn't the longest ranged, but it combined adequate performance in all areas with exceptional dive bombing accuracy, and that combination proved decisive. Japanese engineers after Midway studied captured Dauntless examples and examined the wreckage of shot-down aircraft. They understood the technical features. They recognized the effectiveness of perforated dive brakes, but they couldn't replicate the complete system because their industrial capacity was already fully committed to existing programs, and their tactical doctrine had evolved along different paths. By the time Japan might have developed and fielded dive bombers comparable to the Dauntless in capability, American industrial production had moved on to even more capable aircraft. The war's momentum never gave Japan time to catch up. The strategic lesson transcended specific tactics or technologies. The side that could innovate faster, adapt more quickly, and deploy new capabilities in greater numbers would ultimately prevail. At Midway, the SBD Dauntless represented the American ability to develop effective weapons, train operators to use them skillfully, and employ them in coordinated operations that achieved strategic objectives. The pilots who flew the Dauntless into combat understood they were operating obsolescent aircraft by 1944 standards. Newer, faster dive bombers were entering service, but many veteran pilots preferred the Dauntless precisely because they understood its capabilities and limitations intimately. They knew exactly how it would behave in a 70-degree dive. They knew exactly when to release for optimal accuracy. They knew the sounds the airframe made under stress and could distinguish normal groaning from dangerous structural strain. This accumulated experience made them more effective in the older Dauntless than they might have been in newer aircraft they hadn't mastered as thoroughly. The Dauntless proved that precision mattered more than raw performance, that hitting the target with a single 1,000-pound bomb accomplished more than missing with 10 bombs. That steep diving attacks from extreme altitude could defeat defensive systems optimized for different attack profiles. These lessons remain relevant to military aviation. Modern precision-guided munitions emphasize the same principle. Accuracy defeats defense. The ability to place a weapon precisely on target from any angle, any altitude, any direction, creates tactical flexibility that opposing forces struggle to counter. The perforated dive brakes on the Dauntless in 1942 and the GPS-guided bombs of the 21st century serve the same fundamental purpose. They give the attacker control over the engagement geometry. The Japanese battleships and carriers at Midway couldn't believe American dive bombers were attacking from 10,000 feet at 70-degree angles because their doctrine considered such attacks impractical. The time required for such attacks seemed to create too much vulnerability to fighters and anti-aircraft fire. But American pilots proved the doctrine wrong through systematic training and technical capability. They demonstrated that what seems impossible often depends on having the right tools and the right techniques. The SBD Dauntless gave them both. The results changed naval warfare forever and helped decide the outcome of the Pacific War. One aircraft, one technique. One morning in June 1942, when everything came together and the balance of power shifted irreversibly. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.